Hello everyone, in this lecture I am going to discuss about the time domain analysis. So, in the previous lectures I have already discussed the basics of control system, analogy of mechanical system in the electrical system, and I have discussed about the state space analysis. So, in this lecture I am going to discuss about the time response analysis or time domain analysis of the system. So, what is the time domain analysis? Time domain analysis refers to the analysis of the system performance with respect to the time. It is used to evaluate the state and output responses with respect to the time. So, the time response of control system usually divided into two response, that is transient response analysis and steady state response. So, what is transient analysis? It is defined as a part of the time response that goes to zero as time becomes very large. Steady state analysis, it is the part of the total response that remains after the transient has died out, as this time response analysis deals with the estimation of steady state error between input and output. So, in the steady state analysis we are discussing about the steady state error, and in transient analysis we are discussing about the performance specifications of the system. So, what are the standard test signals which are used for getting the response of the system? So, in most of the cases the input signals to a control system are not known prior to design of a control system. Hence, to analyze the performance of a control system, it is excited by the standard test signals such as unit step signal, unit ramp signal, and parabolic signals, etc. So, what are these signals? Input unit impulse signals. Unit impulse signal is basically denoted as delta t, and mathematically we can write minus infinite to infinite delta t is equal to 1. It means area under the curve is 1. Unit step signal. Unit step signal is defined as ut, and ut is mathematically you can write like this: ut is equal to 1 for t is greater than 0 and 0 for t is less than 0. So, thus this unit step signal shows the abrupt discontinuity at t is equal to 0. What is the Laplace transform of this signal? Laplace transform of this unit step signal is 1 by s, and Laplace transform of impulse signal is 1. Now, before going to the time response, before moving towards the time response analysis or tangent analysis, I would like to discuss what is type and order of the system. So, every transfer function representing the control system has its certain type and order. The steady state analysis depends on the type of the system, and the type of the system is obtained from the open loop transfer function. So, how can I define the type of the system? The number of open loop poles occurring at origin determines the types of the system. So, if the number of poles occurring at origin, or you can say, suppose the transfer function is defined like this: Gs is equal to k dash s plus z1 s plus z2 upon s ki power n s plus p1 s plus p2. So, it is clear from this transfer function that z1, z2, z3 up to zn are the poles zeros of the transfer function, and p1, p2, p3 up to pn is the poles of the transfer function. S ki power n denotes the number of poles occurring at origin. So, this is the type n system. If n is equal to 0, it will become the type 0 system. N is equal to 1, it will become type 1 system. N is equal to 2, it will become type 2 system. So, the number of poles at origin will decide the type of the system. The highest power. Now, how will you define the order of the system? Order of the system is obtained from the closed loop transfer function. Closed loop transfer function is given as gs upon 1 plus gshs. So, from the characteristic equation we can define the order of the system. The highest order of the characteristic equation will give the information about the highest power of the characteristic equation will give the information about the order of the system. So, in one line we can say that open loop transfer function gives the information about the type of the system, and closed characteristic equation gives the information about the order of the system. So, the highest power of the S or highest power of the characteristic equation will give the information about the order of the system, and number of poles occurring at origin from the open loop transfer function will give the information about the type of the system. Let us take an example. Suppose GS is equal to 10 S plus 2 upon S square S plus 5. So, from this equation you have to identify the type and order of the system. So, it is clear that this is the type 2 system because number of poles occurring at origin is 2, and from how will you identify the this is the type 2 system, and how will you identify the order of the system? For identifying the order of the system, we have to write the characteristic equation 1 plus GSHS. It is already written that this is unity feedback system. So, HS is equal to 1. So, 1 plus GSHS is equal to this. So, S ki power 3, highest power of S will give the information about the order of the system. So, this is the type 2 order 3 system. So, from any transfer function, if the open loop transfer function is given, you can define the type of the system from that transfer function, and after writing the characteristic equation, you can comment on the order of the system. Highest power of S will give the information about the order of the system. Now, coming to the transient response analysis. So, consider this is the transfer function x naught s upon xis, where x naught is the output and xis is the input. So, this is the transfer function. If this is a 0 order system, so what will become? It will become B naught by A naught. All the coefficient of S will become 0. So, only the constant will remain. So, B naught by A naught, that is equal to K. So, most of the sensors and transducers are example of the 0 order system, and there is no time response analysis for the 0 order system because the characteristic input output characteristics are linear. Now, coming to the first order system, first order system, in the denominator, or you can say only the S coefficient will be there. So, you can write the transfer function of the first order system x naught S upon xis is equal to B naught upon A1S plus A naught. So, we can write in time constant form. This will give B naught by A naught upon A1 by A naught S plus A1. So, it will give K upon 1 plus Ts. So, time constant, you can define the time constant is equal to A1 by A1 by A naught. So, time constant is defined as the time taken by the system response to reach the 63% of the final value, and pneumatic system, hydraulic systems, thermal systems are the example of this first order system. Systems with only one pole are called the first order system. The systems which are having only one pole are known as or called as first order system. Now, coming to the transient analysis of this first order system. Suppose this is the block diagram of the first order system. The transfer function will be Cs by Rs will be equal to 1 by tau S plus 1. So, what will be the impulse response? Rs should be equal to, if I am talking about the impulse response, so Laplace transform of this impulse signal is 1. So, Ys will be equal to 1 by Ts plus 1 by tau S plus 1 into Rs, 1 by tau S plus 1 into 1 because Rs is equal to 1. So, what will be the inverse Laplace of this? So, Yt will be equal to 1 by tau e ki power minus t by tau. We can write like this, 1 by tau S plus 1 by tau. So, 1 by S plus A is nothing but e ki power minus at. So, this is equal to e ki power minus t by tau, 1 by tau is the multiplier. So, tau is the time constant of the system, and 1 by tau e ki power minus t by tau is the transient response while the steady state term are 0. Now, what will be the step response? So, the process will be the same, the only RS has been changed. So, the Laplace transform of the unit step signal is 1 by S. So, what is Ys is equal to 1 by tau S plus 1 into Rs. So, after doing the partial fraction, we will get this 1 by S minus tau by S tau plus 1. So, what will be the inverse Laplace of this? Yt will be equal to 1 minus e power minus t by 2, t by tau. In this case, we can see that the transient response is equal to minus t by e की power minus e minus t by tau, and steady state is 1. Now, what is the ramp response? Now, again we will consider here Rs is equal to 1 by S square, because the Laplace transform of the ramp signal is 1 by S square. So, you can write here, after doing the partial fraction, we will get this 1 by S square minus tau by S plus tau square by t as tau plus 1. So, after doing this, after taking the inverse Laplace of this signal, we will get t minus tau plus tau e minus t by tau. This is very simple. So, the transient signal will be, transient response will be tau e power minus t by tau, and the steady state will be t minus tau. So, in this way we can define the transient state and steady state response of the system. Similarly, we can do this for the parabolic system. Now, the general equation for the second order system is this: Ys by Rs is equal to omega n square upon S square plus 2 zeta omega ns plus omega n square. So, whenever we are defining the second order system, we will compare with this standard second order system. Let us consider the example for this rotationary system, and this is the example for this electrical system. After comparing these two transfer functions from the standard transfer function, we will get value of omega n, that is natural frequency, and zeta is the damping factor. We can find the value of zeta and omega n by comparing these two transfer functions from the standard second order standard transfer function. In this transfer function, omega n is the natural frequency, zeta is the damping ratio. So, if the transfer function for the rotationary system is defined as Td is equal to J d square theta by dt square plus B d theta by dt plus k theta. So, by taking the Laplace transform of this equation, we can get T ds is equal to Js square plus Bs plus k theta s. Now, what will be the transfer function? The torque is the input and rotational torque is the input and angular rotation is the output. So, what will be the transfer function? Theta s by Tds is equal to 1 by Js square plus Bs plus k. Now, we have to convert this equation into this form. For that, we have to make the coefficient of s square 1. So, for making this coefficient of s square 1, we will take j common. So, this will become 1 by j s square plus b s by j plus k by j. So, now we will compare this omega n square by kj. So, I will get here omega n is equal to under root k by j, and by comparing this 2 zeta omega n is equal to b by j, I will get here zeta is equal to b by 2 under root kj. Now, coming to this electrical network. In this electrical network, it is clear that V naught by VIS. I am interested here in finding the transfer function. For finding the transfer function, we have to find the voltage across this capacitor and input voltage in terms of R, L and C. So, after calculating input voltage and output voltage, we will find the value of V naught upon VIS. After getting the value of V naught by VIS, I will compare this transfer function with the standard second order standard transfer function. After comparing this, I will get 1 by LC is equal to omega n square. So, I will get here omega n is equal to 1 by under root LC, and zeta is equal to 2 zeta omega n is equal to R by L. So, I will get here zeta is equal to R by 2 under root C by L. So, in this way we can find the natural frequency and damping factor for any system. Now, what is the block diagram of this second order system? This is the forward path omega n square upon s plus 2 zeta omega n, and unity feedback is the feedback path. So, what will be the value of Ys by Rs? Ys by Rs can be calculated by using the formula Gs by 1 plus GSHS. We can calculate using this formula. So, Gs upon 1, after putting this value, Gs is equal to omega n square upon s plus 2 zeta omega n, and Hs is equal to 1. By after putting these values, I will get omega n square upon s square plus 2 zeta omega n s plus omega n square. Now, coming to the system parameters. What is damping ratio? Damping ratio is zeta. It is a dimensionless quantity describing the decay of oscillation during a transient response, and basically it is the ratio of actual damping to the critical damping of the system. So, natural frequency omega n is the angular frequency at which the system tends to oscillate in the absence of damping force. And what is the damped frequency? Angular frequency at which system tends to oscillate in the presence of the damping force. So, mathematically we can write omega d is equal to omega n under root 1 minus zeta square. So, this is the relation between natural frequency and damped frequency of the system. Now, what are the responses of the second order system? Response of the second order system mainly depends on the damping ratio. So, for any test input, the response of the second order system can be studied in 4 cases depending on the damping effect created by value of zeta. If zeta is greater than 0, then it is known as overdamped system. If zeta is equal to 1, then it is known as critically damped system. Zeta is in between 0 and 1, then this is underdamped system, and zeta is equal to 1, then this is undamped system. Now, what is the impulse response of the second order system? So, impulse response, we have to take the input as an impulse signal. So, what is the Laplace transform of the impulse signal? Laplace transform of the impulse signal is 1. So, what will be the value of Ys? Ys will be equal to omega n square upon s square plus 2 zeta omega n s plus omega n square. So, zeta is equal to 0 will give the undamped system. So, if zeta is equal to 0, then what will happen? Omega n square upon s square plus omega n square. So, which type of system we will get? Yt will be equal to omega n sin omega n t. So, the Yt will be equal to the sine wave, which is oscillatory function. If zeta is less than if zeta lies between 0 to 1, then the response will be equal to this. Omega Yt will be Ys will be equal to omega n square upon s square plus 2 zeta omega n s plus omega n square, and Yt will be equal to this. Then this is also a sine wave signal with the exponential signal. So, the response will be like this. Yt is equal to omega n upon under root 1 minus zeta square e power minus zeta omega n t sin omega dt. Now, case 3, zeta is equal to 1, then the response will be like this, and the impulse response and in time domain will be Yt is equal to omega n square t e power minus omega n t. If zeta is greater than 1, then Ys will be equal to omega n square upon s square plus 2 zeta omega n s square. If zeta is greater than 1, then we will get Yt is equal to this. So, the response of the system will be like this. So, in this case, we can see that in case of zeta is less than 1, the output is oscillating near this response is oscillating near the output, or we are approaching towards the output. But in case of these systems, zeta is greater than 1 or zeta is equal to 1. Zeta is greater than 1, the response is sluggish in nature. So, in case of step response, we can similarly find the in case of step response, we can see the effect of zeta on the response of the system. So if zeta is, if in case of a step signal, Rs is equal to 1 by s, and what will be the output ys? Ys will be equal to omega n square upon s square 2 plus 2 zeta omega ns plus omega n square. So ys will be equal to, by making the partial fraction of this, we can get ys is equal to omega n square. By putting this zeta is equal to 0, we will get omega n square upon s square plus omega n square. After getting this, we will do the partial fraction of this. After doing the partial fraction, we will get 1 by s minus s upon s square minus omega n square. So we want the value of yt, so for which we have to take the inverse Laplace of this ys. So yt will be equal to 1 minus cos omega n t. So it is clear that the response of the system will be like this. Similarly, for case 2, we can do the analysis for zeta is less than 1. So in this case, we can see here ys is equal to omega n square upon s square plus upon s square plus 2 zeta omega ns plus omega n square. So if I take the inverse Laplace of this, so what we have to do? We have to do the we have to do the partial fraction like this. So we will, if we do the partial fraction, we will get here 1 by s minus s plus zeta omega n upon s plus zeta omega n square plus omega d square. So from where we are getting this, we are making the whole square by using omega d square. See here, s square plus 2 zeta omega ns plus omega n square, we are adding here omega d square and subtracting here omega d square. So what will I get here? S plus zeta omega n whole square, s plus zeta omega n whole square plus omega d square. I mean to say, if I am writing here, I can write here omega d is nothing but omega n under root 1 minus zeta square. So after calculating, after making this whole square, we can get 1 by s minus s plus zeta omega n upon s plus zeta omega n square plus omega d square. So after taking the inverse Laplace, I will get here yt is equal to 1 minus e minus zeta omega nt cos omega dt minus zeta upon under root 1 minus zeta square e minus e की power minus zeta omega nt sin omega dt. So after doing this, after taking the Laplace, inverse Laplace, we can see here this is in the form of sin a cos b plus cos a sin b. So we can write here e की power minus zeta omega nt upon under root 1 minus zeta square is, we are considering here this is sin theta cos omega dt plus cos theta sin omega dt. If sin theta is equal to 1 minus under root 1 minus zeta square, then cos theta will be equal to zeta. So we can write here sin omega dt plus theta. This is nothing but sin a plus b. Sin a plus b is sin a cos b plus cos a sin b. So we can write here 1 minus e की power minus zeta omega nt upon under root 1 minus zeta square into sin omega dt plus theta, where theta is equal to cos inverse zeta is equal to sin inverse 1 minus under root 1 minus zeta square. Now we can see here this is equal to this and we are getting this. Now for zeta is equal to 1, we are getting here again Laplace inverse of this omega n square upon s plus omega n square. After putting this zeta is equal to 1, we will get here s square plus 2 omega ns plus omega n square. This is nothing but the square of this s plus omega n square. So by taking the partial fraction, we will get 1 by s minus 1 by s plus omega n minus omega n upon s plus omega n square. So what will be the inverse Laplace of this? This will be equal to yt will be equal to 1 minus e power minus omega n t minus omega n t e power minus omega n t. So this is the step response. So these are the step response comparison of the various characteristic equation roots located in the S plane. If the plane is located, if the roots are located in the left side of the S plane, it means zeta is greater than 1 and the response will be like this. If zeta is equal to 1, then the roots will be on the, two roots will lie on the real axis. If zeta is lying between 0 and 1, then roots will lie on the S plane, or you can say lie on the S plane means the roots will be complex in nature. So the response will be like this. If zeta is equal to 0, then the roots will lie on the imaginary axis and the system will be unstable. And if zeta is greater than minus 1, the roots will lie on the right side of the plane, then the system will become unstable. In this case, you can say it's the only two roots are lying on the imaginary axis, or you can say if the roots are lying on the imaginary axis, then you can say that the system is marginally stable. If double roots are lying on the imaginary axis, then you can comment that the system is unstable. Here in this case, last case, you can see here the roots are lying on the right side of the S plane, it means the system is unstable. So this is all about the time domain analysis of the system. I will discuss the frequency domain analysis in the next lecture. Thank you.